the gaseous states.
I will continue the explanation about the states of matter. Yesterday you learned already about solid and then also liquid. We know there are some structures, example like uh, simple molecular structure, giant molecular structure, and then also lattices, ionic lattice, and then giant ionic lattice. And now we are going to study about the ideal and real gases. There are some assumptions of the ideal gases. The first, the gas molecules move rapidly and randomly. Number two, the distance between the gas molecules is much greater than the diameter of the molecules, so the volume of the molecules is negligible. And then all collisions between particles are elastic. This means that no kinetic energy is lost in collisions, or in other words, the kinetic energy is the energy associated with the moving particles. And then the last, temperature of the gas is related to the average kinetic energy of the molecules. A theoretical gas that fits this description is called an ideal gas. In reality, the gases we encounter do not fit this description exactly. Although they may come very close, the gases we encounter are called as real gases. Noble gas, such as helium, neon, krypton, they are small atoms. They approach to ideal gas behavior, but they are not called as ideal gas. So they approach to ideal gas behavior because the intermolecular forces are very small. Like in this one, the assumption ideal gas, no intermolecular forces. But in noble gas itself, the intermolecular force are very small. And then ideal about about the ideal gas. Scientists have taken accurate measurements to show how the volumes of gases change with temperature and pressure. This shows us that gases do not always behave exactly as we expect an ideal gas to behave. This is because real gases do not always obey the kinetic energy theory in two ways. The first way, there is no zero attraction between the molecules. And then the second, we cannot ignore the volume of the molecules themselves. These differences are especially noticeable at very high pressures and very low temperature. So, in order to make this one, the real gases into ideal gas at high pressure and very low temperature. Under these conditions, the molecules are close to each other. And the second, the volumes of the molecule is not negligible compared with the volume of the container. There are van der Waals or dipole forces of attraction between the molecules. Attractive forces pull the molecules towards each other and away from the walls of the container. The pressure is lower than expected for an ideal gas. The effective volume of the gas is smaller than expected for an ideal gas. This one we can describe in general equation. So this one we are learning about the ideal gas. ideal gas and real gas. In this world, there is no such ideal gas. Ideal gas is only a theory with some assumption. Real gas is something that we have in our daily life. Okay, now about the calculation of ideal gas. In calculation of ideal gas, we have to use an ideal gas formula. For an ideal gas, we can combine the laws about how the volume of gas depends on temperature and pressure. We also know from that the volume of a gas is proportional to the number of moles present. Putting all consider all this together, there is a general formula of the ideal gas is becoming P times V equals to nRT, where P equals to pressure, V refers to the volume, and then N refers to amount of moles of gas, and then R refers to the constant. The constant is 8.31 Joule Kelvin per mole. Okay, and then there is a Boyle's law, and then also Charles law and Gay-Lussac law. What are those laws represent, or what are those laws called as? In Boyle's law, the volume V is of a fixed mass of a gas at constant temperature is inversely proportional to the pressure on the gas. That's why P times V equals to constant. That is Boyle's law. So in this one, usually refer to the pressure one. There is a first condition and second condition, where the volume of a fixed mass of gas at constant temperature is inversely proportional. So in here, we have to have the constant temperature. Different pressure makes different volume. Okay. Now the next law. Charles' law, or called also Gay-Lussac law. The volume of a fixed mass of a gas at constant pressure is directly proportional to its temperature. In here, two conditions with the same number of pressure. So, volume divided by temperature is constant. And then, what are the units of the things that in here? Pressure. The unit of pressure of a gas, or we start defining pressure of a gas is the force it exerts on a given area of its container. The SI unit of pressure is Pascal. 1 Pascal equals to 1 Newton per meter square. Okay. And then beside using Pascal, we can use also ATM. 1 ATM equals to 1 times 10 to the power of 5 Pascal. And then next, about the other volume, the volume is in meter cube. We know the SI unit of volume is meter cube. And then the K equals here is constant. Temperature can be in Kelvin. We know the standard, the SI unit is Kelvin. And then amount of moles of gas is moles. So let me repeat again about the ideal gas and real gas. So there are assumptions. Okay, the molecules of ideal gas behave as rigid spheres. There are no intermolecular force between molecules of an ideal gas. The collisions between molecules of ideal gas is perfectly elastic. That is, there is no loss of kinetic energy during collision. Like just I told in the beginning about these assumptions, and the last assumption, the molecules of an ideal gas have no volume. Okay. And then so there how are the some real gases behave? The behavior of some gases compared with an ideal gas, we may expect that real gas depart from ideal gas behavior because the molecules are different shapes and size. Okay. Of course, in the textbook you have to read again. There are many explanation and then about the ideal gas. You will get more deeper understanding when you read about this real and ideal gas, and then we are going to have practice on the intermolecular forces, also the structures, and then the concept of real and ideal gases, and then also the calculation of ideal gases. Okay, so after this we are going to have an exercise. You may ask question if you have doubt after this presentation.
Okay, regarding the theory, solid liquid gas, in the theory of solid liquid gas, who has question? Who has question? Solid liquid gas, especially this part about the slide 7 and slide 8. Does anyone have question? Why are you so quiet? How about Billy? Is there any question, Billy? Hello? Billy? Are you there, Billy? Or just your name? Okay. Wait. Oh, so today many participants, usually only 8. Okay. Now let me ask Atta. Is there any question, Atta? Hello, Atta. You have any question regarding the theory? Andrew?
No questions.
Okay. I'm glad to hear your voice. Okay, so now before I continue with the exercise, let me take attendance. Let me take attendance. Let me take attendance of grade 11B. 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 Yes, this one. Okay. So in 11B, Alicia is never present. Alicia never present. And then Alberto just not so active, also very passive. And then there is Andrew. Andrew is here. And then Atta is here. Billy. Billy is here. Brian is here. Carlton is absent. So Alicia, Alberto, Andrew, Atta is here. Carlton is absent. And then Eiffel is here. Hayato here. Janice here. Then Kayla is here. Kevin P, Kevin N, Mario, Matthew, Matthew, Matthew is not here. Matthew P, and then Maximilian also not here. Nia. Oh, what happened with Nia? Nia was here. Rizky never present. Saka never present. Sarah. Saka only one or very seldom. Sarah also very seldom. Shannon is not here. Valentino is absent. Okay. So let me open if there is no question regarding this one. So let me put it back. Yeah. Okay. And then we go with the exercise. I put already this exercise on the Google Classroom. Okay, I put this one already on Google Classroom. We just need you just need to open it. Okay, and then for this exercise number one. Okay, let me move this one here. Okay, number one. Diamond and graphite are both forms of carbon. Diamond is able to scratch almost all other substances, whereas graphite may be used as a lubricant. Diamond and graphite both have high melting points. Explain each of these properties of diamond and graphite in terms of the structure and bonding. So the question is clearly asking about structure and bonding. Give one other difference in the properties of diamond and graphite. Let me ask to Kaila. Hello, Kaila.
Yes, teacher.
Yeah. What is the bonding with what is the chemical bonding in diamond and graphite?
Wait. Diamond is covalent.
Yes, graphite.
Graphite is also covalent.
Yes, correct. So the bonding, both of them are covalent. Now let me ask to Hayato. Hello, Hayato. Are you there, Hayato?
Yes, yes,
Yeah. What is the structure of diamond?
Wager.
Yes. What is the structure of diamond and what is the structure of graphite? Yes. Yes. Hayato? What is the structure of diamond and graphite?
Bang.
Yes. Yes. Hayato?
It, wait. Is this covalent carbons?
Yeah. Diamond is covalent bonding. Kyla already
Yes.
told us. Uh, and graphite also covalent bonding. But what is the structure of diamond?
Okay, wait.
Yes, Hayato? The structure of diamond is giant molecular structure with tetrahedral. And then for graphite, also giant molecular structure but with uh, hexagonal layers. Hexagonal layers means there are three bone pairs. 3 bond pairs with only half lone pair. The half
Okay.
the half lone pair is considered to be a free electron. This free electron responsible for the electrical conductivity in graphite. The question asks for give one difference in the properties of diamond and graphite. It is the electrical conductivities in graphite. While in diamond does not conduct electricity at all. Okay. So for this exercise, we continue again tomorrow. Tomorrow you have to prepare with answer. Then tomorrow I'll ask each of you questions. Okay. Okay. So good afternoon, students, and we will see each other again tomorrow.
Thank you, teacher.
Yes.
Sure.
Yes.